The Big Bang was not a space event. It was space itself exploding. The Big Bang theory is a mathematical model of the universe's expansion. It proposes that, roughly 13.8 billion years ago, all of space, time, matter, and energy were concentrated in an unimaginably hot, dense state. Not a point in space, but space itself compressed to near zero volume. And then space began to expand, not into anything but as a stretching of the fabric of reality itself. This expansion continues today, with galaxies not flying through space, but being carried apart by the expansion of space between them.
There was strong evidence for this model. In 1929, scientist Edwin Hubble made the most famous evidence when he saw that light from faraway galaxies was redshifted, which means it was stretched to longer wavelengths. This meant that they were moving away from us, and the universe was getting bigger. Your mind will take you back to a time when the universe was smaller, denser, and hotter, until you hit a singularity. In math terms, that's what the Big Bang theory is all about.
Over the next few decades, more data supported the idea. Scientists found the cosmic microwave background radiation, CMBB, by mistake in 1964. The CMBB is a weak glow of microwave light that comes from all directions in space. This was seen as the cooled remains of the hot, dense, early universe, which supporters of the Big Bang had forecast many years before. Then readings were made of hydrogen, helium, lithium, and other early light elements. The number of them was about right for nuclear fusion in the early moments of a hot universe that was growing quickly.
All of this led to a remarkably successful framework. A universe born in fire, expanding ever since, cooling, and gradually forming stars, galaxies, and eventually life. The model worked so well that it became standard cosmology, adopted into textbooks, simulations, and global consensus. But despite its success, there were always gaps.
The horizon problem was one of the issues. This is the question of why the universe looks so consistent when different parts of it should never have had time to share knowledge or energy. Another one was the flatness problem, which asked why the universe's shape looks so much like a flat surface. The monopole problem asked why we don't find traces of the high-energy particles that should be there if the universe really did start the way we think it did.
To solve these, cosmologists proposed a tweak in the 1980s called cosmic inflation. It posited that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially faster than the speed of light. This inflation would have smoothed out irregularities, stretched space flat, and diluted unwanted relics. It became an add-on to the standard model, not part of the original Big Bang theory, but now inseparable from it in most modern versions. So today, when scientists say Big Bang, they're usually referring to a composite theory, an initial singularity, followed by rapid inflation, followed by slower expansion, cooling, the formation of hydrogen and helium, the release of the CMBB, and finally the emergence of structure. It's important to note that the Big Bang theory doesn't try to explain why the universe began or what came before. In fact, in the traditional view, time itself began with the Big Bang. There is no before. The theory also doesn't say much about the true nature of the singularity, because at that point our equations break down, quantum effects dominate, and general relativity loses its predictive power. This is where the James Webb findings become so unsettling. The theory predicts a slow, gradual emergence of structure from chaos. Galaxies should form over time, stars should evolve through known fusion processes, and everything should align with the timelines set by the cosmic microwave background and redshift measurements. But if Webb is seeing galaxies that are too old, too big, and too organized too soon, then that timeline may be wrong. And if the timeline is wrong, then the basic ideas that redshift, distance, and age are based on might also be wrong. That means the universe's age, or even the rate at which it is expanding, might be wrong. Even worse, what we think we know about space, time, and light might not be full, which would make our whole model of the universe shaky.
Strange galaxies in Hubble's deep field. Astronomers have known for a long time that galaxies were acting badly, even before the James Webb Space Telescope sent back its jaw-dropping pictures. The Hubble Deep Field, which is one of the most famous sets of pictures ever taken, gave us the hints. With telescope time, what started out as a risky bet turned into a new way to see into the past.
In 1995, astronomers pointed the Hubble Space Telescope at what seemed to be a completely empty patch of sky. No stars, no galaxies, no obvious targets, just darkness. They kept the shutter open for 10 consecutive days. What they found stunned everyone. Thousands of galaxies densely packed into what appeared to be nothing. Each smudge, each spiral or fuzzy arc was a galaxy, some over 10 billion light-years away, meaning we were seeing them as they existed near the dawn of time.
Astronomy was changed by this one picture. It told us that there were a lot more galaxies in the universe than we had thought. Some people thought that by looking deeper into space, we could see earlier and earlier steps of how the universe evolved. This proved that idea.
Over the years, Hubble would use this method over and over again, creating the ultra-deep field and the extreme deep field, which got closer and closer to the theoretical limit of what could be seen. But as the resolution improved and the redshift data accumulated, something strange began to emerge. Some of the galaxies in these deep field images appeared too evolved for their apparent age. They had complex structures, spiral arms, bulges, and even signs of rotation. These weren't the chaotic, irregular proto-galaxies expected from simulations of the early universe. These looked like mature galaxies.
And yet, according to redshift calculations, they existed just a few 100 million years after the Big Bang. At first, these were just thought to be random outliers. It's possible that the galaxies were being mistakenly named. Their light might have been distorted by gravity lensing, or maybe it was just a fluke. A few odd cases that didn't hurt the model as a whole. But the unease didn't go away.
A lot of studies came out, and they all said the same thing. Galaxies appeared too early, stars had metal contents that were not expected, and black holes were too heavy for their age. Even though the basic model was still the best, it was taking hits.
The problem came down to cosmic timelines. According to the Big Bang framework, it should take hundreds of millions of years for gravity to draw together gas into stars, for those stars to live and die, and for their remnants to form more complex systems. Heavy elements, what astronomers call metals, are produced in the cores of stars and scattered by supernovae. So, the early universe should have been metal-poor and structurally primitive. But some Hubble Deep Field galaxies defied this expectation. They seemed chemically enriched, tightly bound, and rotationally stable. A case from a galaxy called GNZ11 was one of the most convincing. Hubble saw GNZ11, and spectroscopy later confirmed it. It looked like it existed only 400 million years after the Big Bang. It was as heavy as a billion suns though, and it showed signs of star formation at a speed that shouldn't have been possible at that point. Not only was it surviving, it was growing.
Still, astronomers remained cautious. Hubble's capabilities, while groundbreaking, had their limits. The deeper it looked,
the harder it became to resolve faint galaxies from noise. And infrared sensitivity, crucial for detecting very distant red-shifted objects, wasn't Hubble's strongest suit. What was needed was a telescope that could look deeper more precisely and with an eye tuned to the cool, stretched light of the early universe. That telescope would be James Webb.
But what's critical to understand is that Webb's most shocking discoveries didn't come out of nowhere. The seeds of the current cosmological crisis were already planted in the deep field images. The signs were there of galaxies evolving too quickly, stars forming in unexpected environments, and mass accumulation happening faster than any current model predicted.
The way science deals with these kinds of contradictions is what makes this change so strong. To begin with, the material is not believed. Then it is looked into, questioned, and often added to ideas that already exist. But at some point, when the strange things start to add up and can't be explained away any longer, science will have to change. What started out as a few strange galaxies in a deep field picture may now be seen as the first cracks in the Big Bang's base.
Too many mature galaxies, too soon. Not only did the James Webb Space Telescope take stunning pictures of the universe, it also showed us a huge problem with how we think about cosmic time. The Big Bang model gets stronger with each early huge galaxy that Webb finds. As a way to make sense of the results, scientists suggested that early galaxies might have been more efficient than modern ones, for example, by using their gas stores more quickly. But that just puts things off. How could that level of efficiency appear so quickly, in such large numbers, and over such large areas of the early universe? Also, why didn't models say it would happen?
Another theory suggested that perhaps dark matter clumps in the early universe created deep potential wells, allowing matter to collapse faster than expected. But even this tweak struggles to explain the sheer number of massive galaxies Webb has found. And it doesn't account for the metallicity and organized structure seen in so many of them. If the timeline of galaxy formation is off, it might mean our measurements of distance, based largely on redshift, need to be re-examined. It might also mean that time in the early universe functioned differently than we assume, or that the cosmic expansion model itself needs updating. Perhaps the laws of physics we observe today didn't hold exactly the same way when the universe was young.
These questions are now rippling through astrophysics, like shockwaves. The standard model of cosmology, known as LCDM, lambda cold dark matter, has long been considered robust. It accounts for expansion, the cosmic microwave background, large-scale structure, and more. But James Webb's findings are testing the edges of that confidence. Some scientists have even called the early results a crisis in cosmology, one that demands either serious revision or radical reinterpretation.
Meanwhile, the Webb telescope continues to deliver. Every new image, every deeper exposure seems to reveal yet another galaxy that's too big, too old, or too fast to fit the timeline. And while researchers are hard at work refining measurements and testing alternatives, the broader picture is hard to ignore. The early universe looks far more like a cosmic metropolis than a construction zone. It's still too soon to say whether these discoveries will overthrow the Big Bang theory entirely. Paradigms don't collapse overnight, but history shows us that when observation contradicts theory, the burden is on the theory to adapt.
Redshift reconsidered.
One of the most important ideas in astronomy is the idea of redshift. It tells us how far away something is in space. That's how we plot time. And it's the very thing that tells us how far away and how far back in time a galaxy is. But now that James Webb has found new things, some scientists are starting to wonder, did we get redshift wrong?
To understand the weight of that question, you first have to understand what redshift is supposed to tell us. When light travels from a distant object through the expanding fabric of space, it stretches just like the sound of a receding ambulance lowers in pitch. The wavelength of light increases as its source moves away from us. Blue light becomes redder, hence the term redshift.
In cosmology, redshift is also used to track cosmic expansion. The higher the redshift, the farther away the object is, and, crucially, the further back in time we're seeing it. An object with a redshift of 2 is being observed, as it was when the universe was roughly 3 billion years old. An object at redshift 10, that's from when the universe was less than 500 million years old. The higher the redshift, the closer we are to the Big Bang. We use this relationship to build the entire cosmic timeline, from the formation of stars and galaxies, to the appearance of black holes, even to the rate of universal expansion.
In essence, redshift isn't just a measurement. It's the backbone of cosmic history. The galaxies observed at extreme redshifts, values of 10, 11, 12, and beyond, aren't behaving as expected. They're too big, too evolved, too structured, as if they've had far more time to grow than the timeline allows. One explanation is that these galaxies are somehow younger than they appear, that their brightness, mass, or structure is misleading. But another, more radical possibility is that our interpretation of redshift is flawed. Could it be that redshift isn't telling us what we think it is? That perhaps cosmic expansion isn't the only, or even the correct reason for why light gets stretched over vast distances?
This is not a new question. In fact, it's one of the oldest controversies in cosmology. When Edwin Hubble first saw that galaxies were redshifted and looked like they were moving away from us in the early 1900s, some scientists came up with other ideas for why this might be happening.
The tired light theory was one of the most famous. It said that photons lose energy by interacting with particles or fields in space, which makes them redder. In that view, redshift would not show that something is expanding, but that photons are getting tired after traveling long distances. That theory fell out of favor for lack of supporting evidence and for failing to match certain observed features of the universe, like the precise spectrum of the cosmic microwave background. Still, Webb's findings are giving new life to old questions. If expansion alone can't explain the strange maturity of high redshift galaxies, is there something else affecting how we interpret redshift?
On a higher level, there are also theoretical theories that question redshift. Some scientists think that space-time might not be smooth, especially in the beginning of the world. Light might have redshifted in ways we don't understand right now, if space-time curves or quantum fluctuations were stronger in the past. Others say that light might combine with dark matter or energy in ways that change its frequency over billions of years. Still others point to the possibility that light behaves differently at quantum scales, meaning redshift could be influenced by factors that aren't part of the standard model at all.
If space is granular, if time is emergent, or if the speed of light itself has changed over cosmic history, then everything we assume about redshift might be built on a moving foundation. There's also the unsettling realization that much of our redshift calibration depends on models we're now questioning. We use redshift to estimate distance, but we also use models of galaxy evolution to infer redshift. This circular logic becomes dangerous when the very models that interpret redshift are being challenged by the Webb data. It's too early to throw out redshift entirely. The idea remains one of the most predictive and consistent features of cosmology, but the precision with which we equate redshift to time and distance may need recalibration. It might be that redshift does indicate expansion, but not in a linear one-size-fits-all way, or that in the earliest epochs, something unknown distorted the relationship we've come to trust. The impossible stars. The first generation of stars, the so-called population 3 stars,
was supposed to be seen by the James Webb Space Telescope. These stars are big, hot, and mostly made of hydrogen and helium. These were supposed to be the first light sources in the universe. They were supposed to have been born in a world that was clean and free of heavy elements.
Instead of finding the long thought to be primordial stars, Webb has found something very different, stars that shouldn't exist that early and formed in a way that doesn't fit with the normal model of cosmology's timing and chemistry. What Webb found were massive, luminous stars embedded in ancient galaxies, radiating intensely not just with hydrogen and helium, but with clear signs of metallicity.
In astrophysical terms, metals refer to any element heavier than helium, carbon, oxygen, nitrogen, iron, all of which are formed in the hearts of stars and scattered by supernova explosions. The presence of these elements in early stars implies that several generations of stellar birth and death had already occurred, but Webb is seeing these enriched stars just a few 100 million years after the supposed Big Bang. That leaves almost no time for multiple generations of stars to live, die, and recycle their materials into more complex offspring.
This shouldn't be happening under the Big Bang framework. The first stars form after cosmic recombination, when electrons and protons combine to form neutral atoms, and the universe cooled enough for gas to clump under gravity. These population 3 stars, if they existed, would live short, violent lives, exploding in brilliant supernovae and paving the way for second and third generation stars enriched with heavier elements.
But this process takes time, hundreds of millions of years, if not longer, to build up the levels of metallicity we're seeing in stars that appear to exist. Webb's discovery of stars with high metallicity at such extreme redshifts poses a serious problem. It doesn't just suggest early star formation, it suggests early chemical evolution at a speed and scale that current models can't replicate.
In galaxies like GNZ11 and CS 1019, stars appear to be not only burning hot, but chemically complex. That complexity requires a stellar life cycle that should be impossible within such a short cosmic window. Some experts have tried to explain this by saying that stars formed very quickly in the early universe. It's possible that the conditions in the very first galaxies made it possible for stars to form, live, and die much more quickly than was thought before. They might have been denser, cooler, or had crashes caused by shock waves that start the chemical cycle right away.
But this idea isn't logical because Webb isn't just finding one richer star or galaxy, it's finding a lot of them. This common trend makes it seem like the early universe wasn't a blank canvas, just waiting to be drawn, but
What's
a
even
scene that was
stranger
already full
are
of details.
stars that are too big for existing theories to understand. Based on Webb's findings, some of the stars may have masses hundreds of times bigger than our Sun, which could be close to the theoretical upper bounds. The usual view is that big stars are unstable, and the radiation pressure should break them apart or make them fall into black holes. But in the early galaxies Webb looked at, huge stars not only seem possible, but also common. These impossible stars shine with such luminosity and complexity that it's hard to imagine them forming without some precursor conditions. But there shouldn't have been enough time since the supposed origin of the universe for those conditions to exist. Even accounting for gravitational collapse and rapid cooling, the interval between the Big Bang and the formation of these stars is alarmingly short. What if the universe didn't start with simple hydrogen clouds and a clean slate? What if instead the early universe was already chemically active, already building stars with metals, already forming systems more advanced than we expected? That would suggest a very different origin, or at least a different pacing than the Big Bang theory allowed.
Some strange ideas like plasma cosmology or steady-state models say that the universe is endless or circular and that matter and energy are always changing instead of being created in a single event. These points of view say that early stars aren't really early, they're just a part of a process that happens over and over again in the universe. These models haven't been used in a while, but Webb's results are giving them some attention again. There's also the chance that our entire model of stellar evolution is missing something. Perhaps the physics of the early universe allowed for faster fusion, quicker lifespans, or exotic stellar behaviors we don't yet understand. Maybe dark matter played a catalytic role. Maybe there's an unknown factor influencing how stars are born, live, and die. But until those gaps are filled, we're left with a universe that seems to be cheating the rules. The stars that were supposed to be impossible, too massive, too old, too enriched, are not only real but common, and they're rewriting the story of how light returned to the cosmos.
Ancient black holes, where there should be none. People often think of black holes as the grim reapers of the universe. They are the dense, collapsed remains of very massive stars, or the enormous monsters that lurk at the centers of galaxies. Their birth is not simple or quick. Black holes are thought to be the end of time in the standard model of astronomy. To form, live, and die, they need generations of stars. They want mass, mergers, and brutal, slow construction. They are, however, being found everywhere by James Webb. Way too early and way too big. Supermassive black holes, those with millions or even billions of times the mass of our Sun, are normally associated with well-evolved galaxies. Our own Milky Way hosts one, Sagittarius A, sitting calmly at the center, a gravitational anchor that formed over billions of years. But Webb's observations are detecting active galactic nuclei, AGN, the bright energetic signals of material spiraling into black holes in galaxies that exist less than 700 million years after the Big Bang.
Some of these black holes already appear to have masses in the hundreds of millions of solar masses, and that timeline is a problem. This is not something that can be done quickly. It takes time. Even if you start with a seed black hole, which would be the remains of a very large population 3 star, maybe 100 solar masses, it would have to keep growing through accretion and collisions with other galaxies in order to become supermassive. It takes hundreds of millions to billions of years for that process to finish, even in the most hopeful models. Webb, on the other hand, sees them fully grown before the universe was formed. This isn't just early black hole formation, this is early black hole domination.
Some of the host galaxies appear to be centered around these giants, suggesting that black holes were not just a consequence of galaxy formation, they may have been a prerequisite. That flips the traditional model on its head. Sears is one of the most shocking examples. It is a live galaxy with a giant black hole that was around when the universe was about 570 million years old. Even more amazing is that it looks like it is accreting matter, which means it wasn't inactive and was actively eating gas and changing its surroundings. This is the kind of behavior that galaxies usually show when they are much further along in their growth.
Some scientists have proposed that these black holes formed from direct collapse, an alternative mechanism where massive clouds of gas collapse directly into a black hole without ever becoming a star. This would create larger seed black holes from the start, allowing them to grow more quickly. But even this theory struggles to explain how such seeds could be in place and already accreting so early, especially in galaxies that are also forming stars rapidly. To grow so quickly, these early black holes would need not just mass, but an abundant fuel supply, cold gas, dust, and matter falling in at just the right rate. But such smooth, rapid feeding contradicts many of our models, which assume turbulence, feedback, and fragmentation would slow the process. And yet Webb is finding these monsters already formed and active, quietly violating every timeline we thought we understood.
Even more concerning is the number of early supermassive black holes. They're not rare gems. They appear to be common features of early galaxies. That implies a universal process, not an exception. And that in turn suggests something far deeper might be wrong with our assumptions. If black holes this massive existed so early, it changes how we understand structure formation, star formation, and even reionization, the process by which the first light sources transformed the universe's opaque hydrogen fog into transparency. Black holes, through their energetic radiation, may have played a far larger role in shaping the early cosmos than previously thought. Some people are even starting to think that black holes might not be the end of evolution, but the beginning. Some models now think that primordial black holes, which didn't form from stars but straight from quantum changes in the very early universe, might have been the first things that led to the formation of galaxies. Black holes didn't wait for galaxies to form around them. In this version of events, it was around the black holes that the galaxies formed. It's an unsettling reversal, and it forces cosmologists to confront uncomfortable possibilities. If supermassive black holes are this ancient, this common and this central to galactic life, then maybe our universe didn't evolve in the slow, linear fashion we imagined. Maybe it sprang into complexity faster than we thought possible. Or maybe it always had.
Dark matter in crisis. Dark matter has been the universe's quiet framework for decades. It is the mysterious material that makes up more than 80% of all matter in the universe and holds galaxies together. It does not give off light, reflect light, or interact with the electric force. But its pull on the universe can be felt everywhere. That's what we thought anyway. The James Webb Space Telescope is here. Webb's study of the universe's oldest galaxies and structures has not only raised questions about how old and how big these things are, but it has also started to question the framework that these things are meant to hold together. However, when we use dark matter models on Webb's data, we find something very troubling. The math doesn't add up. The standard cosmological model known as LACDM, lambda cold dark matter, relies on the idea that dark matter clumped together early in the universe, creating gravitational wells into which normal matter could fall. This clumping is what supposedly triggered the formation of galaxies, stars, and eventually planets. Dark matter wasn't just a background player.
On the other hand,
first actor
Webb's
on the stage.
observations of
But
some
Webb's
galaxies
observations are now
show that they
suggesting that
depend
large,
less on dark
well-structured
matter than was
galaxies
thought.
appeared far
The spectral
earlier than
data we
ACDM
use to
allows.
figure out
If
their
these
mass
galaxies had
distributions
dark
and spin
matter
shapes
halos, which
don't
they must,
always match
according
up
to the
with
model,
what we would
then
expect
those
from
halos
dark
would need
matter.
to form extremely
These galaxies
rapidly,
act
more
like they're held
rapidly than the
together by
model
less
permits.
unseen
In other
matter
words,
than the
if
model
dark
says
matter
they
was
should
doing
be.
its job in the early
This isn't the
universe,
first time dark matter has raised eyebrows. Even in the nearby universe, some galaxies like NGC 52 DF2 have appeared to contain virtually no dark matter at all, defying the expectations of galactic formation theory. But these were rare, localized puzzles. What Webb is showing is that the earliest galaxies, supposedly shaped entirely by dark matter, are not behaving as dark matter-dominated systems should.
The way the structure is spread out is another point of tension. It takes time for dark matter to gather into clumps in CDM. In the beginning, the universe should have been mostly smooth, with small changes over time turning into strands, nodes, and gaps. But Webb is finding galaxies that are not only closer together, more lined, and sometimes more orderly than theory says they should be. Without highly developed dark matter support, there shouldn't be this much order. But where did the order come from if the dark matter didn't have time to set itself up in those ways first?
perhaps dark matter behaves differently than we thought. Maybe it's not as cold as LCDM suggests. If it's warm or self-interacting, it might clump faster or distribute itself differently. But these modified versions of dark matter create their own problems and don't fully align with other observations, such as those of the cosmic microwave background or galaxy cluster dynamics. Second, it may mean that alternative gravity theories, long considered fringe, need to be re-examined. Models like MOND, modified Newtonian dynamics, or TAVIS, attempt to explain galactic rotation and structure without invoking dark matter, instead modifying how gravity works at large scales.
These theories have struggled to explain all observations, especially on cosmological scales, but Webb's revelations may provide new ground for hybrid models that blend modified gravity with limited dark matter.
Third, and perhaps most radically, it could mean that dark matter, as we conceive it, simply doesn't exist, or at least not in the form we've theorized for nearly half a century. Maybe our gravitational equations are incomplete. Maybe our understanding of mass and energy in curved space-time is flawed. Or maybe we're missing a layer of physics entirely, one that Webb is beginning to expose, not with direct evidence, but through persistent mismatch between prediction and reality. The most important thing about this problem is that dark matter isn't just a placeholder in our models. Modern astronomy, astrophysics, and particle theory are built on top of it. In some ways, it even explains how galaxies form and how the universe is structured. Dark matter is needed for the dominoes to fall. If it fails, dark matter is not being directly found by James Webb. It can't. But by pushing the edges of what can be seen in terms of time and resolution, it is trying. What would happen if dark matter existed? And those effects are looking more and more stressed.
So, cosmic inflation. Far reconsidering cosmic inflation. For a long time, cosmic inflation has been seen as one of the best ways to explain the universe. It was a bold addition to the Big Bang theory when it was first put forward in the early 90s. It wasn't part of the original framework, but it was needed to fill in some of its biggest gaps.
The main idea behind inflation is that the universe grew very quickly and exponentially just a few fractions of a second after the Big Bang. Space grew bigger than the speed of light for a very short but important moment, stretching the universe flat, smooth. Inflation was introduced to solve problems. The horizon problem, for example. Why does the universe look the same in every direction, even though distant regions shouldn't have had time to exchange light or information? Inflation says, because those regions used to be in contact until inflation blew them apart.
Then there's the flatness problem. The universe appears to be geometrically flat, which should be extremely unlikely. Inflation says that's what happens when you inflate a small, curved patch of space. It flattens out. Neat, clean, mathematically clever.
But there's one thing inflation didn't do. It didn't make any direct, testable predictions when it was first proposed. It was speculative, and for years, it remained on shaky ground. Later refinements gave it more mathematical rigor, and its predictions, especially about the spectrum of cosmic microwave background fluctuations, lined up remarkably well with observations. That cemented inflation's role in the cosmological mainstream. It became standard doctrine.
However, inflation has always had a strange air of creativity about it, a fix on top of a workaround. With the help of early data from James Webb, the questions that inflation was meant to hide are now coming up again. Webb isn't looking at inflation straight on. That event would have happened about 10 seconds after the Big Bang, which is so early that not even light had come into being yet. But Webb is looking at the shape of the universe in its early stages, which is a result of that time of inflation. We notice that the building looks too well put together, too perfect, and sometimes too old.
The more we see of it, the galaxies that Webb is detecting aren't just forming earlier than expected. They seem to appear fully formed, with large masses and ordered spins, as if they didn't evolve through chaos at all. This is problematic because inflation was designed to explain structure by introducing small quantum fluctuations into a smooth early universe. These fluctuations then seeded the growth of galaxies, stars, and clusters.
But what happens when that structure appears almost instantly without enough time for fluctuations to evolve? The paradox is reversed. Inflation was meant to introduce just the right amount of irregularity into a very smooth universe. But Webb's early galaxies seem to skip the irregularity entirely. They suggest a universe that went straight from inflation or something like it into complexity.
That either means inflation operated very differently than we thought, or it didn't happen at all. Inflation predicts a very specific spectrum of fluctuation, with certain sizes of structure being more common than others. Yet the cosmic web, even at early times, seems to exhibit a puzzling uniformity, one that doesn't align neatly with inflation's output.
If that trend holds, it could indicate a deeper inconsistency between the predictions of inflation and the universe's observed evolution. On top of that, there are philosophical problems. Even though inflation is useful from a mathematical point of view, it has worrying effects. A lot of the time, this leads to the idea of a multiverse, which means that inflation didn't happen just once, but keeps happening forever in some places, creating an infinite number of tiny worlds. By definition, these worlds can't be seen. That means the theory is very hard to disprove and very close to philosophy, which is a very bad thing. Webb's findings bring us back to a crucial question. Did the universe really need a brief moment of unthinkable expansion to explain its current state? Or were we using inflation to cover for gaps in a model that never worked as smoothly as we believed?
Some researchers are beginning to revisit older ideas, like bouncing or cyclic cosmologies, where the universe didn't start from a singularity at all, but from the collapse of a prior universe. Others are exploring quantum gravity frameworks, where space and time
The
are
Big Bang
emergent
model,
phenomena, and the
it was
need for
thought that the
inflation
early
disappears
universe would be
entirely.
mostly smooth, but with some small flaws caused by quantum ripples that were stretched into small changes in density. These tiny variations were critical. They were supposed to be the imperfections that allowed structure to form. A completely smooth universe, after all, would remain smooth. Galaxies need gravitational irregularities, bumps and clumps of matter to pull together gas and stars. Without these flaws, there's nothing to assemble into stars, planets, or us.
In fact, these imperfections are visible in the cosmic microwave background, CMB, showing up as faint temperature fluctuations, the fingerprints of those early seeds. The CMB shows those tiny changes as expected, but James Webb's pictures of the early universe don't seem to show the chaos that those seeds should have caused. Webb is looking at a universe that is too smooth, too symmetrical, and too calm to find signs of a universe that is still putting together its structure.
This isn't the ease that comes from being the same everywhere. It's not that galaxies are spread out evenly. They're showing up in places, numbers, and shapes that are hard to predict. It's more that the rate and organization of structure creation look too clean and advanced for how soon after the Big Bang they're happening. Galaxies are showing up with spins that are in order. Clusters are coming together in a very consistent way. Things aren't as messy as they should be, which is disturbing.
According to the inflationary model, the fluctuations should have produced clumpy distributions in the early stages of the universe. Regions of higher and lower density gradually collapsing into increasingly complex arrangements. Webb, however, is detecting galaxies that seem to have bypassed the chaos. In some fields of view, there's a surprising uniformity in size and shape. Structures that should have formed over billions of years seem to be already in place, just a few 100 million years after the Big Bang.
This problem is similar to what some scientists have said about inflation, that it fixed too many problems that were present in the world at the start. Inflation may have made the universe too smooth by stretching space so quickly and efficiently, leaving not enough room for structure to grow in the way we see it. The galaxies we see with Webb shouldn't exist. if that's the case. Still, there they are. Some have proposed that our understanding of early gravitational collapse might be flawed. Perhaps gas and dark matter coalesced faster than expected. But this too has limits. Gravitational systems need time to grow, even if you crank up star formation efficiency or hypothesize unusually cold dark matter. It doesn't easily account for the scale of the structure being observed.
Others point to the possibility that our cosmological simulations used to predict how structure should have formed may be oversimplified. Perhaps the universe doesn't evolve the way we've been programming our models. But if that's true, it calls into question the reliability of decades of predictions built on those models, including the very shape of the early universe.
There's also the potential that the smoothness is an illusion, that we're seeing galaxies that formed unusually early due to unknown physics, while the rest of the universe lagged behind. But the more Webb surveys the early cosmos, the harder this is to sustain. The anomalies are becoming too common to be rare flukes.
Another cosmic puzzle that is related to the too smooth problem is, why is the structure of the universe on a big scale so perfectly balanced? How is it that the rate of growth, the spread of matter, and the curvature are all so perfectly lined up for galaxies to form in the first place? Scientists thought that inflation would explain this, but Webb's results show that the accuracy might be even higher than inflation suggests. It's almost like the world knew exactly what it was doing.
What if the early universe wasn't a mess that eventually birthed order, but something closer to a ready-made system? A cosmos that didn't build complexity, but began with it already encoded? That would require a reimagining not just of structure formation, but of the universe's initial conditions, or the absence of a singular beginning altogether.
James Webb, the impossible early galaxy problem. It was only a matter of time before someone said they were impossible. This can't be meant in a poetic or figurative way. It's just not possible according to normal physics. The James Webb Space Telescope's first deep field pictures showed these galaxies that don't look like they should. They are too big, too bright, too old, and most unsettlingly, there are too many of them for any place on the Big Bang time frame to fit.
Astronomers expected Webb to find primitive objects, small, chaotic, gas-rich clouds in the process of becoming galaxies. They expected to see the messy beginnings of order, stars just igniting, and structures forming slowly over hundreds of millions of years. What they found instead were fully formed galaxies, shining at redshifts of 10, 12, and even higher, galaxies that existed when the universe was just a few 100 million years old. These galaxies weren't merely surprising because they were there. They were impossible because of how much they had already accomplished. Some contain as many stars as the Milky Way, others have well-defined disks, stable rotations, and chemical enrichments that suggest they had already undergone several generations of stellar evolution. They didn't look like babies, they looked like adults, living in a toddler universe.
Webb saw a galaxy called Sirius 9316 that has a redshift of about 16.7, which means we are seeing it as it was only 240 million years after the Big Bang. This is one of the most striking cases. Models that are already out there say that this galaxy shouldn't have had enough time to make even its first set of stars, let alone grow up. Still, there it is, clear, organized, and shining.
The reason these galaxies are labeled impossible isn't just because they're early, it's because the timeline for how long it takes to form stars, build mass, and organize into complex structures is grounded in well-understood physics. Gas clouds take time to cool and collapse. Star formation requires density thresholds and gravitational instabilities. Metal enrichment requires the birth and death of multiple generations of stars. These are not processes that can be rushed. And yet somehow, these galaxies seem to have done it all within the first 2% of the universe's lifespan. When Webb began returning its early data, many assumed that some of these galaxies were being misidentified, that their redshifts might be overestimated due to photometric confusion or contamination by nearby objects. But as the spectroscopic confirmations began rolling in, the reality set in. These redshifts were real, and so were the galaxies.
This has led to a growing chorus within the astrophysics community. Something about our model is broken. Some theorists have proposed revising star formation rates, assuming these early galaxies were much more efficient at converting gas into stars than modern ones. Others suggest a new class of ultra-dark halos that might have accelerated collapse.
But these patches only go so far, and they raise new problems. If star formation was that efficient, why don't we see similar behaviors in more recent cosmic history? If mass collapsed that quickly, what does that say about the nature of dark matter or the influence of unknown forces? And perhaps most fundamentally, why didn't our models predict this? That's the question that keeps resurfacing. For decades, cosmological simulations have guided our expectations for what the early universe should look like. We built a framework, the LCDM model, that told us when galaxies should form, how large they should be, and how they should evolve.
But Webb has pulled back the curtain and revealed a stage already full of players before the play was supposed to begin. It's not just that these worlds are there that makes people feel uneasy. It means that our whole idea of how the universe is put together may be wrong in terms of time.
What else did we get wrong about the early universe? If it wasn't a slow build-up of complexity, but a quick jump into it?
No time for evolution. Why the early universe looks ready-made.
Modern astronomy is based on the idea that things get more complicated over time. Galaxies don't just appear like light bulbs turning on, they change over time. They begin as clouds of hydrogen and helium, stick together because of gravity, give birth to their first stars, get more material through the death of stars, and slowly change into the moving structures we see today. It is thought that this process of the universe growing up from simple to complex will take billions of years.
But the James Webb Space Telescope has a different view, one in which the early universe didn't change slowly over time. It came into being fully formed. In every deep field image, James Webb is finding galaxies that look complete, not on their way to becoming something, not assembling already there, with star formation rates that rival modern galaxies, with disks, bulges, and spiral arms, with chemical signatures that suggest multiple generations of stellar recycling. These aren't rough drafts, they're polished chapters, appearing just a few 100 million years after the supposed Big Bang.
According to our models, the cosmic dark ages, the period between the release of the cosmic microwave background and the first stars, should have lasted around 200 to 300 million years. During this time, the universe was cooling and gravity was slowly beginning to work on the first neutral atoms. After this phase, the earliest stars and galaxies were expected to begin forming, messy, metal-poor, and small.
But what Webb is showing instead is a universe that seems to have skipped the awkward adolescence altogether. Some of these galaxies have stellar masses comparable to the Milky Way. That means they would have needed to form stars at breakneck speed, turning gas into suns with an efficiency that no current model supports.
Even the most aggressive starburst scenarios, events that trigger rapid star formation, can't explain how galaxies this big could exist this early. If galaxies form so quickly and completely, it means our timeline for cosmic evolution is wrong, possibly by orders of magnitude.
It raises the uncomfortable possibility that the universe wasn't a slow unfolding narrative, but something preloaded with structure, just waiting to be observed.